Welcome! In this lesson, we explore green chemistry through energy minimization principles in solvent-free mechanochemistry. We will cover the chemical picture of how the reaction happens, the mathematical energy landscape, a simple statistical model of collisions, and then summarize all of this with clear graphs. Part 1. Chemical mechanisms. Inside a ball mill, solid reagents A and B are hit repeatedly. Each impact injects mechanical energy, creating transient high-energy sites and enabling new bonds to form directly in the solid state. We can summarize the overall scheme as a plus B going to an activated complex, followed by products, with no solvent present. The sequence at the particle level is fourfold. 1. Fracture and fresh surface creation. 2. Collision-induced bond distortion. 3. Formation of the new bond between A and B right at a solid-solid interface. 4. Relaxation to products with minimal energy lost to a solvent cage because there is no solvent. Here is a schematic bond formation step. A has an available electron pair. It attacks B while the B to Y bond breaks. The result is the A to B bond and the leaving group Y. This captures the same logic as solution mechanisms, but the activation energy is delivered by impact. Part 2. Mathematical principles. We describe the energy along a reaction coordinate as a baseline, then a barrier, then a product well. Mechanical impacts inject energy per collision and effectively raise a mechanical temperature, leading to a rate constant proportional to the collision frequency times an exponential of minus delta E double dagger over K B times T effective. Part 3. A simple statistical model. Treat each collision as a Bernoulli trial. The success probability per collision is the exponential of minus delta E double dagger over K B times T effective. The probability of at least one successful activation in n collisions is 1 minus P to the n. If the number of collisions is proportional to milling time, the yield often follows 1 minus an exponential in time. Now, let us graph the ideas. First, an energy profile versus reaction coordinate. We highlight the transition state and the barrier height delta E double dagger, and show that products can sit lower than the reactants. Next, yield versus milling time. Many solvent-free reactions follow a rising exponential trend, leveling off near completion. We show example data and a simple fit that encodes the effective rate constant. Finally, a histogram of collision energies with a smooth Maxwell-Boltzmann-like overlay at an effective mechanical temperature. The right tail of the distribution provides the fraction of collisions energetic enough to cross the barrier. To summarize, solvent-free mechanochemistry minimizes energy wasted to solvents, channels impact energy into the reaction coordinate, and leads to kinetics controlled by the collision distribution and an effective mechanical temperature. Chemical mechanisms, mathematical energy landscapes, and statistical collision models all align with the graphs we have drawn.